On this episode of Pipeline Things, we take you to Centreville, Virginia, a place you might not have been, but in a scenario you might find yourself as an operator. If I asked you, how many times do you excavate dents? And if you don't find anything, or if the final deformation after the dent re-rounds is less than reporting criteria, do you just recode it and move on? What if I told you there's certain situations where that might not be the best idea? Hang on as we take a look at the NTSB's failure investigation into Colonial Pipeline in Centreville, Virginia. It's a good one. Thanks. I do a little thing like you do? Yes. All right. So, we never ever realized
you just noticed that, right?
I did. I did not notice that until we did the 1 year anniversary high five episode. Cool thing.
Why don't you pay attention to me more often, right?
I think it's because the intro for our audience is actually more difficult to pull off than you realize. We have to navigate not knocking over
all kinds of stuff.
Miss Aaron Rodgers. Is that what we call it? I don't know. We gotta.
No, because that was terrible.
Yeah, I know. The Aaron Rodgers.
4 plays. Wasn't it 4 plays when he was out?
No, we can't go with Aaron Rodgers anymore. Even though she said turf won't stop her, Miss Producer will get a different name. We're gonna have to go with something else.
We have to come up with something good.
Yeah, but it's harder to navigate all the stuff and sit down after you do a high five. So I never ever paid attention to your little riff that you do after. So
when you love somebody, you know everything about
song?
them.
When you love someone.
Yeah, and you should know everything about me. And you didn't even do like I do like a little thing.
You're an idiot. Okay, so you know what season it is, Chris? Not fantasy football. Don't say it.
It is fantasy football.
It's running season right now.
It is also running, and it's been hot.
Yeah.
In the H.
Dude, it's so bad in the morning right now. And my daughter, Aubrey, my second one, she's doing cross country, right? Yeah. So I have to watch her.
It builds character.
It does build character. I'm actually really proud. She is struggling through cross country in every sense of the word.
We all struggle. For the record, we all struggle through cross country. It's just at what point do you begin to struggle?
I don't think my kids. I didn't bless them with mental toughness. Like I did it myself whenever I did a half Ironman. I struggled through it, but I have my own struggle coming up. So I'm running a Ragnar race. I don't know if I told you about this.
Yeah.
That
sounds amazing, to be honest with you.
It's the worst game of relay ever.
It's not worse. I mean, it makes you feel more, there's more like...
Well, the name Ragnar makes you think, let's go like 300, man, grab some swords. But racing for 24 hours... Are you going
to wear just like the little underwear-looking type shorts, like the 300 guys in like leather sandals?
No,
dude, that would be so cool. No. Do you think someone will? It's Ragnar races. Do you think someone will wear like the leather sandals?
There are people
with
that
like the underwear looking.
Some people do them in full blown outfits. Some people do it to podium. Not me. Other teams will do it like fully dressed up. So,
dude, we legitimately need to consider this next year.
We need 6 more people. You want to take the whole? This could be an announcement. I hope our team members, so we're a team of 7 now. I hope that all of our D2I colleagues recognize, you'll have 1 year before we do the Ragnar race in San Antonio next year, and you have to be able to run 15 miles in a 24-hour period. Is that what we're telling them?
All fully outfitted. How cool would that be? That could be a fundraiser. Like if we got so much, like we would have to do it and give it to our local charity.
Yeah,
that would be cool.
Right now, I'm just thinking it was a bad decision, honestly. What I'm thinking
about. So back to Aubrey. Aubrey's great. Hey, Aubrey, cheers to you for taking this on.
Oh, yeah, absolutely, man. So, but it's funny because, running is it's like one of those things you just have to do it. And like you have to make yourself get up and go run. Like you really have to be diligent.
But, I also ran cross country in high school.
You never thought you just played soccer.
No, I used it for strength and conditioning. So I ran cross country in high school. Then we practiced 3 days a week, games on Saturdays and Sundays. And so I felt like, well, why not run cross country? Point is, I'll give you my perspective on this. I liked cross country because it was organized and there was a start and an end.
Isn't that every race ever created in humankind has a start and an end?
But for example, like when we just get up to go run as part of our daily health, like, I'm going to be honest with you, my goal changes all the time.
Oh, no, I know what I'm getting into before I start the run.
See, that's my thing, right? It's like, I'll wake up and be like, dude, it's 1:07 and it's 2 o'clock in the afternoon. I wanted to do 5 miles. I'm going to do 2.5 today. So I totally changed the rules of the game. Whereas, like, when you're in a race, you're in. Like, I get to determine when I stop. Monday through Friday. On Saturday, you don't get to pick.
It goes both ways too. Yeah, again, I've walked the last 5 miles of a 70.3, and that's a miserable experience. I was wishing that one would have ended
And
early.
Embarrassing.
Oh, it was so bad.
Is that when you just lay over like the soccer players, just start rolling? Oh, medic!
I should have.
Have them get the cart.
Oh, I was so angry at that race. Anyway, so we're continuing on our NTSB arc that we're doing here today, Chris, and this failure is interesting. For our audience out there, we're going to be actually taking you to the events in Centreville and in 2015, dealing with a leak in a liquid pipeline. It's probably more famous than most people actually realized at the time, I would say.
Or the impacts,
the impacts of it, were probably more famous than what most people would have known. But what's funny is this NTSB report is, like, normally they're 70, 80, 100-page monsters.
Yep.
This one's not. It is honestly very straightforward and to the point. So story time with Rhett might be a little bit condensed today, is what I'll say. But what I do want to remind everybody...
So everybody has to switch their audio from 1.5 to back to 1?
Yes, because it'll be a little bit shorter. In contrast to the 1 hour long episode that we did, following Kalamazoo, this one is obviously much shorter. But the reason that I say everybody is probably aware of this episode is most Americans aren't aware of the pipelines around them at all.
Yeah, we've talked about this a couple times.
I know, right?
Yeah.
This one brought them to the front. And the reason why is that this actually involves a pipeline that is crucial to the transportation of refined products from the southern part of the United States. It feeds into one of the pipelines, I should say, that's crucial to the transportation of refined products in the eastern United States. And the failures in this system actually resulted in gas prices increasing on the East Coast.
Yeah. So a lot of people knew about this because now it wasn't about that happened to them. Now it's like it happened to my pocket.
It's like, what? There's a pipeline that has to move product from the south part refineries to the East Coast? Yes, there is. Yeah. And that actually plays a role here. So I'll take you to Centreville, Virginia. You ever been there?
I don't think so.
I don't think I have.
I've been to Centreville, Texas. It's on the way to Dallas.
Interesting.
Yeah.
Well, this particular case, it's 2015, 12 o'clock. And I think what defines this story, Chris, isn't so much the incident itself as the challenge in finding the cause of the incident. So what happens is it all begins with a 911 call, and somebody says that they smell a gasoline odor. The fire department responds to the report, and it's kind of interesting. It was an employee at a restaurant that called in the 911 call, and they immediately suspect that it's coming from a nearby gas station, right? So they think the next door gas station is either dumping gas into the drains or has a leak in the thing. So they spend all this time for the first 3 hours trying to figure out if it's something related to the gas station. And they rule out the gas station pretty quick. And then they realize, hey, there are 2 fairly large liquid pipelines right next door. Maybe it's from them, right? So they contact Colonial Pipeline in this case. And Colonial spends 3 hours trying to determine if the gasoline odor is coming from one of their pipelines. And there's 2 pipelines in this corridor, line 3 and line 4. Yeah. And these are not little pipelines. These are, from a liquid standpoint, giants, right? These are 36-inch diameter, 281 wall thickness pipelines. Those big diameter, high D over T, which will play a part in it later. And Colonial spends 3 hours, and they're actually not able to determine by looking at their SCADA data if they have a leak. They are doing bar hole testing where they're going along the pipeline trying to find it. They have trouble with the rocky soil, getting confirmation of anything. They can't get the probes deep enough. Long story short, basically over 3 hours, they're not able to confirm if the leak's coming from their pipeline. So they keep this process escalating. So originally it was just the Colonial District Office. It expands from the Colonial District Office to basically a company-wide response about 8.5 hours later. Once corporate gets involved, they decide, hey, we're actually going to do a static pressure test between these 2 block valves, 3 and 4. And when they do the static pressure test, they're still able to not conclusively rule in favor or exclude a leak possible in either pipeline, which is amazing, right? So line 4, they say, hey, we're positive there's nothing on line 4. Are positive there's nothing on line 4, but it's possible we have a leak on line 3. Just possible is all they're able to get to. So next thing that they've been doing, this is where a senior integrity engineer gets involved. So it's kind of cool. They get a senior integrity engineer, and he begins prioritizing locations for them to dig in based on historical ILI. They ended up selecting and excavating 6 dig sites through afternoon. So at this point, they are choosing 6 points based on previous features, appurtenances, valves, anything they have in that area they can go and dig. And around 7 o'clock that evening, so 7 full hours later, they're excavating line 4 and around a dent that had been determined in a previous inline inspection. They find contaminated soil at this location. They keep digging all the way through the night to expose the full pipeline diameter, and then they find product dripping underneath the pipe after they managed to get the full circumference of the pipe uncovered. So it took almost over a day to find the right location, then a full 2 days to completely confirm that they had a leak in the pipeline. And of course, what they do is that they go ahead and they put a sleeve over it temporarily so they can do some other work and move on. But it begs the question, and we'll talk about it a little bit, is 2 things come up to play here. One is the nature of the feature that failed. And I'll go ahead and tell you, because we're going to get into it, it's a dent, right? So we find out that it was actually a dent that failed. Yeah. And then the second question is, well, how did they not know the pipeline was leaking, right? So the NTSB report spends a lot of time on the leak component of this particular pipeline. And I think it's interesting. Our audience may find it interesting to know that they found that the SCADA system, that the leak was actually so small that the SCADA system wasn't able to actually find it. The leak rate was about 0.004% of the total flow. So remember, it's just a big 36-inch diameter pipeline. But even that tiny amount of flow was enough to obviously contaminate a significant amount of the soil and obviously result in 911 calls and an NTSB report, if you will. And so they determined that, hey, we can't find this in the SCADA system. And it's about that 0.004% is about 550 times lower than the SCADA leak detection limits. So it explained, again, Colonial was off the hook from a sense of being able to detect and identify it. But the dent is really what becomes the real story. Yeah. And so as we get there, before we get in, I want to ask you, Chris. Yeah. Because you were an operator. Yeah. Where were dents on you guys' threat spectrum? You didn't know I was going to ask you this question either.
Yeah. I would say it was fun. I enjoyed dents.
You enjoyed dents?
A little bit.
Where did they rank on the threat spectrum? I mean, you had metal loss, you had SCC.
No, they're high.
They were high?
Yeah, it was high. It was high because I felt like you never knew what you were going to find, right? And so, I mean, let's think about this just in general. That would cover maybe different type operators, right? Back at the time when I was an operator, we would leverage different technologies from run to the other. So an example of that would be, hey, we had a caliper run done on this date with this technology. Now we have a more modern caliper or another MFL. We didn't detect the dent with metal loss previously, but the dent was there. Now we have a metal loss that we can correlate to. So it's dent with metal loss, and we know that code and HCA says you need to dig it. And so as an engineer wanting to investigate things and understand, and as our friend Ted Lasso would say, I like to be curious. So I'd ask a lot of questions.
I thought you were going to say be a goldfish. And I was like, I don't know how that works here.
Maybe that comes up later. Maybe we'll bring that up later. But I'd ask a lot of questions. So I'd call analysts and we'd pull up the data and I would start asking logical questions, right? Is this a deformation or is this a dent? Right?
Well, let me ask a question. Did you have instances where you dug up the dent, found something, and then recoded the pipe and moved on?
Absolutely. And not only that, but I would do my best to leverage that information on future ones. Yeah. Right? So if we found shallow dents at the bottom of the pipe in a certain terrain, that it was a break in the coating and we found light metal loss that was triggering any metal loss associated with a deformation, we'd characterize those, right? So if we saw it was on the shoulder of the dent versus in the dent or the deformation, we would integrate all that and begin to classify them and say, you know what, these are higher priority and these are not.
And I think what you just described actually represents what a lot of gas operators do. Yeah. I think it is actually directly what contributed to the failure here. So let me catch the audience up.
But I will say this: it's also fair for us not to say that that's that common either, right? Because I would say there's a lot of
What's not that common?
It's almost a little bit of the Wild West if you think about it, right?
Oh, Dents?
Oh, absolutely.
Yeah, Dents. I'd say particularly around this time and before time. Even now, we might say that Dents are the Wild West with operators' responses looking different. But what caused this failure? Let me take you back a little bit. So remember, I told you it was a dent.
Yeah.
It turned out that this dent had actually been excavated before 2015. It had actually been excavated in 1994.
Mm-hmm.
That's 21 years later, 21 years earlier, right? The dent had been excavated. It was below the repair criteria. So once they excavated the dent, it might have been deeper before, but once they excavated it, the pipe re-rounds because it was a bottom-side dent.
So if it was constrained or unconstrained?
Yep.
Got it.
So most
re-rounds.
bottom-side dents, the dent re-rounds. This is common.
You said it was rocky, right?
Yep.
So what does that matter?
Because it just explains
what if it was
why
what if it was like a nice farm ground or something like that?
I'd say it's less likely that you're going to get a bottom side restrained dent that would re-round, but it's not impossible either, right?
Okay.
I mean, you could have something as simple as a wooden 2x4 that was left in the trench to support the pipe can create a bottom side dent that when removed will pop out. Yeah. That's what happened in 1994. So they went there to excavate this dent. It re-rounds to around 1.6%. And they're like, hey, regulatory doesn't require us to do anything. Let's move on. I'll say for our audience out there, it has been almost without a doubt proven, not in all circumstances, you can't say it every time, but in most circumstances, when you have a deep bottom side restrained dent, by deep, I mean greater than 3 or 4%, maybe even 2%, and then you unrestrain that dent, allow it to pop back out, and then just rebury it, you've actually made the situation worse when you have the threat of fatigue cycling present, which is this was a liquid pipeline, heavily fatigue cycled. So what happened is over the next 20 years, that dent was now free to flex in a way that it wasn't free to flex before.
Free to flex?
Free to flex.
Or free to flex?
Free to flex. Not free to...
I kind of thought of like Frida's like unibrow, where it's like it pops back out. I feel like
you're making fun of my Louisiana accent that comes out every now and then.
So it's free to flex.
So it's
free
doing
to
flex. Yes, free like this.
Okay.
It's free to flex. Free to flex. And as it does over the course of the next 20 years, it generates fatigue cracks on the outside surface of the dent that grow from the outside surface to the inside surface, resulting in the leak condition that they observed, right?
So is the idea there, and we'll get to more questions later, so is the idea there is that had it not been excavated, it would have had a longer life?
In this particular case, yes. Okay. Or I'd give you another alternative. Had it been preemptively repaired when excavated, it would have had a longer life. The point is that changing the conditions of the dent, and I'll say in fairness, I don't think in 1994 they would have been as aware of this, but we definitely have the research to understand this now.
Yeah.
And the funny thing is, early on in my career, I used to get questions like this from operators a lot. Rhett, if I excavate a bottom side dent and then I don't repair it, did I make it worse? That is actually a common question that I would get early in my engineering career. And the answer is, again, in most cases, yes. So in this case, the NTSB report, it's kind of interesting because we'll get into this more later. They eventually cut the dent out. The NTSB report concludes that it's corrosion fatigue. I thought it was interesting that they labeled it corrosion fatigue. They didn't have a lot of information from the metallurgy report. I think it's fair to say that the corrosion was very, very, very minor. If anything, it might have shortened the fatigue life by giving like an initiation site to the cracks. But this is not metal loss like 20 or 30% or anything like that.
So what you're saying is that
it's predominantly fatigue.
Yeah, so there is a basis of if there's any metal loss there, it can make it worse.
Yes, absolutely.
You just really have to understand.
Right. Unless you have polished steel, anything from polished steel down to light aerial corrosion is going to impact the fatigue life of the dent more than, again, if you had perfectly polished steel. Mm-hmm. So, but you know what? We're going to take a short break right here and come back and let's dive into a little more information on what other things were present in this particular failure. So welcome back. So we're picking up in Centreville, where I'm telling you the story that led to the failure of the dent, right? So again, it's pretty straightforward. This particular dent had been excavated in 1994.
Yep.
They didn't find anything other than a dent. Final depth was around 1.6%.
Yep.
No regulatory criteria requiring them to do anything. Recoded it in the field. I'd say for 1994, that was pretty common.
Yeah.
Shallow dents, so again, it's important to consider that all the depth-based regulation, even up till this time, 2015, is just depth-based, right?
Yeah.
So criteria in both liquid and gas pipelines is really only driven by the depth of the dent.
And what would have been the trigger to want to go after it, right?
Yeah,
It's kind of this whole point of like generally the mentality. If we're going to talk about integrity and not just operations and maintenance, integrity is normally correlating dents to mechanical damage, right? Typically on the upper half of the pipe where something has struck the line. And so, I mean, naturally, I guess we could kind of see where
it wouldn't have mattered.
If there's something on the bottom of the pipe, it wasn't struck. The pipe re-rounds. It looks like it's
After
in good condition.
1994, they continued to pick up this dent and ILI inspections, but it comes back at 1.6%.
Bottom side.
Even if it had been top side, it wouldn't have mattered.
Yeah, but nothing's
it wouldn't have
bothering
classified.
it.
Right. So what we see here is a major gap in regulatory response to dents, right? What comes out and is a bit shocking.
So I guess a question here is it a gap in regulatory response or in integrity engineering analysis?
Well, let's say it's both, because let me give you a little more information. So as PHMSA starts to dig and they recognize, okay, there wouldn't have been...
PHMSA does digs?
PHMSA starts to dig into Colonial's response.
Investigate.
Investigate. I'm sorry.
I got it.
That wasn't even an intended pun. How did you play that way?
I'm just curious.
As they do that, what they find out is Colonial comes to the table and says, yeah, we recognize we're not required to do anything in dents that are less than depth of 2%, but we've had failures in 4 other locations with dents that have depths less than 2%. And so in Pelham, Alabama, Felixville, Louisiana, Simpsonville, South Carolina also had through-wall cracks in the pipeline with depths less than 2%. So this is actually the 4th incident that they've had in a shallow dent.
So do you think that was the trigger for the senior engineer to say, why don't we go look in these locations?
Oh, I'm sure it's probably one of the reasons why they included a dent and where they had looked, they had been looking to find into.
Huh?
Right. And so I think that kind of becomes the crux of this episode, less than the story, but then the impact that it had on dent integrity management moving forward, Chris. And that's where I want to drive the conversation. So one last thought to close it out is I told you that at the time that the incident happened, they sleeved the dent.
Yeah.
Right. The reason they did that is so they could actually run a crack inspection tool. So they ran a crack inspection tool through the pipe, and it was ultrasonic, so UCD because it's liquids, obviously.
Yeah.
And the UCD tool was able to identify the crack in the dent.
UCD?
UCD
stands for what again?
Ultrasonic crack detection.
Okay.
And so, but then after that, obviously they cut it out, and that's what we get today. Right. So again, NTSB makes...
NTSB, what was the recommendation?
Let's get straight to the recommendations work, right? So it says to PHMSA is to work with pipeline trade and standards organizations to modify pipeline dent acceptance criteria to account for all factors that lead to pipe failures caused by dents and promulgate. Such a good word, promulgate.
Pro means like forward.
Could use propagate, could have been initiate, but promulgate? Promulgate regulations to require the new criteria to be incorporated into integrity management programs. So that's the first one.
And we know at the time that IMPs were generally focused on HCAs, which is interesting as well.
And then their second recommendation, which flowed down to Colonial as well, is require operators to either repair all excavated dent defects. That's interesting because that would require some data gathering.
Yeah.
Or install leak detection systems at each location where a dent is not repaired to continuously monitor for hydrocarbons. All right. I mean, that seems a bit impractical, right? If I'm going to have to, unless the dig depth is like really deep or really expensive, it's almost seems like it'd have to be cheaper to dig than install a continuously monitored system. But anyway, and then the third one is they issued a directive to the Association of Oil Pipelines and API. And they said, communicate to your members the finding of this report on the susceptibility of dents to fatigue cracking, even when the dent is under acceptable current criteria. I think I would say even when the dent doesn't fall into regulatory requirements, right?
Lessons learned. So they went to the industry organizations to say, hey, let's try to share this information so we don't get there.
Yeah.
Right? If there's a gap in information that we're responding to in IMPs, then people need to be aware of this. That was a good one. So what happened?
Well, so I think since this time, Oh, we've had definitely a change in the dent landscape. So most people might be aware that Colonial was one of the leaders in the development of API RP 1183, and I mean that standard has its challenges. There have been a lot of people that have raised some I would say both objections and challenges to some of the methodologies in that standard.
Yeah.
But it was absolutely a move towards trying to standardize some of the dent assessment methods. So you see that as number one in API 1183, and Colonial leading the way in some of that. The second thing that you see taking place is, obviously, we already talked about it, is 192.712 and the updated regulations on dents. So there was a lot of talk that PHMSA had wanted to look to 1183 in order to develop that, but to be frank, 1183 took too long, and I don't think there was enough industry consensus around 1183 to actually make it into regulation. So PHMSA kind of did their own thing in 192.712.
So that's some good background. So let's stand it up a little bit. So let's structure the conversation. So if we are to look at, like we always like to do, right? We look at liquid regs in 195 and gas regs in 192. I feel like we're kind of seeing them converge a bit.
Yeah.
We talked a little bit in some of the other episodes we've done where it kind of seems like we now see that maybe because of the regulatory process, how long it takes, we're seeing regulators reference one code and one language, i.e. gas on liquids and stuff because of the rulemaking process. So maybe they're coming together. But at this point, and for our audience, I mean, let's kind of clarify this. What is the biggest discrepancy between 192 regulation on dents and 195 as it stands today?
Well, as it stands today, there is no real difference, to be frank. Not appreciable, right? Yeah. Both standards are depth-based. Both standards are interaction-based. Okay. That's where they go. So again, I'm excluding the proposed ECA process for dents, which is still proposed, is my understanding, is not in final adoption yet.
So we'll go this way. We'll say it this way. So I think the way we say it is and let's break it down. So if you're a liquid guy and you're dealing with pipeline integrity management, you're in 195.452. And if you go to paragraph H, you see these are all the prescriptive things that you need to respond to in dents.
It's all depth-based.
So it's all depth-based, right? Yep. Where it is on the pipe, and is there something interacting with
it,
right?
And again, I've said it multiple times in many publications I've done.
Yeah.
All things being equal.
Yeah.
Depth-based has some merit. Deeper dents are typically more susceptible to fatigue, all things being equal. The challenge is all things are never equal, right?
Okay, so let's unpack that. Why does depth matter, right? Because we have integrity engineers, maybe they haven't applied the mechanics yet or whatever it may be. Why are deeper dents worse?
Again, all things being equal, if you have two unrestrained dents, the deeper one will generally be more severe.
Okay.
Generally. If they're the same length, same diameter, same wall thickness, then the deeper one will be more severe.
And you said restrained, so break that
I said unrestrained. So unrestrained. So dents come in two flavors, right?
Yeah.
Dents come in the restrained flavor, which is not free to flex. Something is holding it in place and pinching it. Free to flex, yes.
Yeah, okay.
And then your unrestrained ones are free to flex, right? Okay. Which means they're nothing.
Unrestrained. They're not being held down. They're not being held together.
And again, it's often used synonymously with constrained, or restrained. I prefer the restrained definition, but both are used interchangeably in the industry.
Okay.
So
that was we kind of referenced 452. So if we look at the gas side, traditionally we look at subpart O 933, which is the sec 192.933 to find your response criteria. Same thing, right?
Same thing. It's
depth-based. Yep. And or you're interacting with something. And it's fair to say that we understand if it's interacting with something, why does that matter? So if you have dent with metal loss, what do you think is the basis for why all of a sudden that's more a higher risk to integrity?
Well, so if we say, again, dent with metal loss has a greater possibility of being associated with mechanical damage, but we can shelve that. Let's shelve the mechanical damage concern and just deal with this threat.
Yeah, because that wasn't what happened here.
Yes. It's that corrosion in of itself would reduce the fatigue life in an unrestrained dent. Interaction with a long seam would reduce the fatigue life. These are all things that would reduce the fatigue life. So the origins of the depth-based regulation are twofold, right? I think it's important to recognize that around this time too, you do have PRCI who's been doing a substantial amount of full-scale test work that I was involved in very early on, even at Struss, around the dents and their fatigue life. But that work's ongoing. It hasn't
been for a long
culminated in a
time,
report.
right?
Yes, it went on for a very long time. Started in 2009 and wasn't completed until like 2017.
2009, and that was what MD
49.
Yeah, MD. Is it fair to say that was probably mechanical damage?
Yes, absolutely.
Okay, so if you guys want to Google that PRCI MD program, starts with 4.
But before that
MD4.
testing, you have to go all the way back to Joe Fowler and Chris Alexander together actually at Stress Engineering did some very early work that gave way to, I think it was the API standard 1153, if I'm not mistaken, which was Bottomside rock dents. It was later recalled.
Okay.
But in that document, they basically confirmed some of what appears in regulation, namely that fatigue of dents that wasn't really a threat in gas pipelines if it was under 6%. So that's why that 6% criteria kind of appears in there. But again, it was limited testing, and generally
but it was empirically based, is what you're saying.
It was empirically based, and a lot of that confirmed that again, deeper dents typically have lower fatigue lives. The challenge is this pipeline I told you is a different animal.
Yeah.
Most liquid pipelines, 8, 10, 12 inch
smaller
diameter, heavier wall, right?
Diameter to thickness ratio.
Bingo. You end up with an 8-inch line that's got, a quarter-inch wall. That only has a D over T of 42.
Yeah.
Right? You take this pipeline here, 36 divided by 281, we're actually up over the hundreds, right? And when that happens, the fatigue becomes much more susceptible. So that's why I say a 2% dent in an 8-inch pipeline, you can probably live with. A 1.6% dent in this pipeline, you can't live with, right? So that's why depth is, so there's so much, I think.
So there's a couple of things you're unpacking for us here, right? It's kind of, this is hopefully not, people aren't listening to 1.5 and they're at the 1, so we can kind of break this down a little bit, right? So traditionally we think about dents. Normally our minds potentially go through mechanical damage, right? And that's not necessarily the case here, right? Where mechanical damage.
You have a time-dependent failure mechanism.
Yeah, we would almost say depth is almost could be argued independent if you're dealing with mechanical damage, right? Because you're maybe dealing with cold work, some strain hardening, initial cracking. So depth at that point maybe doesn't matter. So that's one mindset. This mindset is a little bit different, right? I think what you're saying here is you can have a dent independent of how it got there, top or bottom. The threat is fatigue.
Yes.
And so depending on how your pipe is able to manage the fatigue or address the fatigue and any additional concentrators of stress, i.e. a weld or corrosion in this case. So for example, when I was doing this, we weren't really concerned about fatigue.
And that's common with most gas operators.
I'll say this, right? If I had a dent with metal loss, I'd look at the signals. If I saw it was on the shoulder, it was very light, I would say, hey, they probably broke the coating system. We've got a little bit of mild corrosion here. I'm not really worried about this.
Yep.
That's not the case here, right? So if you have a dent with metal loss, I mean, walk us through that. What's the thought process through dents with metal loss in a liquid line where you're susceptible, or even a gas line where you're susceptible to fatigue?
So I think in both cases, and we've seen that change. So 192.712C now requires fatigue, and I'm gonna say, look, 9 times out of 10, fatigue is going to be a check the box operator a check the box operation for a gas operator. Yeah. I have yet to come across a gas pipeline that has fatigue cycling in any sense of the word, like a liquid pipeline.
I got a question for you. I'm going to break your thought here. Have you done analysis on more than 10 dents? Have you done a high level 3 type engineering analysis on more than 10 dents?
Yeah, I'm trying to think where you're going here. Yeah.
Have you done it on 100 dents?
100 individual level 3s, probably getting close to that, I'd say.
Okay. Any trend?
I've analyzed, but again, when we talk about stress concentration factors, I don't consider that to be a full level 3.
Yeah.
I've done thousands of those, so I've had my eyes on thousands of dents.
Okay. So
that's not exaggeration, because I know we did at least 2,500 at one point in time.
Okay, because what I'm trying to get to is I'm trying to qualify you a little bit for the approach to if I have an interesting situation where I have a high D over T, I have a dent that's either potentially restrained or constrained or it's unrestrained. This process of vetting, because again, when I look at this failure, I think you had somebody with their hands on this that saw it and said, I don't think this is an integrity issue.
Yeah.
So at what point do you start identifying that you have an integrity issue?
Look, I think it's dealing with a couple of things were unique here. One, the dent had previously been excavated and wasn't repaired. So as an operator, if you know you had previously excavated dents that weren't repaired, those are a threat, right? And I'm going to say that even in gas pipelines, they're potentially not a good deal. And you say, well, why, right? If that gas line ever changes service or changes operations, then you have potential challenges there, right? So, but in a liquid line for sure, if you have previously excavated dents where the practice or the MO was just to leave it, recoat it and move on, I think that's potential. The higher your D over T, the greater your potential.
So is the risk in that it re-rounded, so there was some material property changes, or just that you've now allowed it to become susceptible to fatigue?
Again, if the dent is held in place, if it's restrained,
Yeah.
the failure mechanism will still be fatigue, but the fatigue has to grow from the inside surface. The cracks generate on the inside surface and grow to the outside surface. That's how we know restrained dents fail. Let me say the damage accumulation is lower for the restrained dent if it's like, let's just say 4%.
Sure.
Then if you allow it to re-round and you don't subject it to a hydro test or force it any additional re-rounding, that dent that re-rounds under, let's just say MAOP or MOP,
Sure.
that dent is now going to be free to flex, and its fatigue susceptibility would be much higher than it was when it was restrained.
I think we've driven that home.
We have, I hope so, driven
That's the goal. Right?
Yes.
Hear it 3 times, maybe it stays.
So
okay, so now we know if you dig dents and you
whether you're gas or
reround them,
liquid,
you should repair them.
I
and
think
so what
it's
does that
always good
repair begin
practice.
to look like?
I think the only way you don't is if you literally can't see it anymore, right? So I've had operators that have come in and say, "Hey, look, I redug the famous rifle, right? It's like I hear bam,
Yeah.
and then I can't find it." If you literally reround the dent and you can hold a straight edge to the pipe and you can't find it anymore, I'm not going to say install a sleeve or install a composite wrap.
Sure.
But if you excavate the dent and you can still see the deformation, I would just say, hey, do your operators and the public service. I mean, you already got the ditch open. The expense is already
done the
there.
majority of the expense.
Wrap it or put a steel sleeve on it and make sure you fill it with a compressible material. If you do that, you will have probably checked off, honestly, everything that you would want to learn from this particular NTSB failure report. So
what if you dig it up and there is cracking? What do you do?
So, I mean, most operators, if you dig it up and it's cracking, you're probably going to look at excavating and get it out of the pipeline. If it's a critical line,
By getting it out, what do you mean?
I mean, cutting it out, right? So cutting it out. I think most operators would choose to cut it out. You're not bound to do that. I mean, you could put if I knew it had cracks in it, my personal recommendation would be a steel sleeve. That's what I would go with in that case, with, again, a sound filler material in the sleeve. And you would mitigate most of the fatigue growth that you would expect if you did that at that point.
Yeah, I think probably worth considering if you can buff it out too.
Yeah.
Right. So do some MPI, get some phased array, try to get an appreciation for how deep it is. If your operating procedures allow you to buff it out, I would say probably consider that, because at that point, go ahead.
Well, I was going to say, no, it's an important point because operators ask me that, but you said you found a dent with a crack.
Yeah.
Again, I mentioned a lot of times restrained dents, not a lot of times, restrained dents, the cracks will grow from the inside surface of the pipe.
Yeah.
So if you excavate a restrained dent and don't find any cracks, that may not mean you're out of the woodwork. I often tell people you need to get phased array or something that can inspect for cracks.
MPI and phased array, right? Clarify, right? So if you do some kind of phased array or some other crack detection into E technology to understand what's going on. You always want to understand what's going on before you start buffing.
Exactly.
Right.
And then obviously you couldn't buff what's on the inside surface. Yeah. But let me ask you a question.
Yeah, what's up?
If let's say you were a liquid operator and I dumped this on you and you went back and looked and you're like, yeah, we probably have at least 300 deformations that we historically excavated and just recoated.
Okay.
What do you do with this? Do you just go and start digging all of them up? What do you think about the potential to use ILI?
Yeah.
Since we're the ILI guys.
So I'll be honest with you, right? So first and foremost, if I'm an operator, I've got a time constraint and I've got a program that I'm already trying to deal with, and this is probably being dropped on my lap. And my favorite lifeline is phone a friend, right? So I would get on the phone and I'd start calling a bunch of people, right? I would start understanding what records do we have from in the field when we found it. You won't, at least my experience at the time still remains that a lot of the field crew are still in place. And so you can call those guys and say, hey, I'm looking at a dent that's across County Road, picking something 133. It looks like using Google Maps, it's about a mile north of there. Like, dude, yeah, I remember that dig. That was 12 years ago.
Yeah, I didn't find anything.
What was it? Exactly. But that begins to allow you to begin to understand the gravity. Now, are you going to get on the phone and call all 300? No, but I would say I'd phone a friend, understanding what's going on in the field, what records I have. I'd probably call a guy like you and say, hey, this is the ILI data I have. I need to start building a program. I will tell you this. It's normally going to turn into some kind of program. And then what I would do is I'd turn to industry to see what kind of work has been done so I could try to start risk ranking these. And I would probably go to something that you brought up. You brought up API RP, a recommended practice 1183. I'd phone a friend and say, hey, I've got 300 of these. How would you help me start risk ranking these?
And honestly, from there, it actually gets a bit easier, right? So I'd say if you did that, you'd be in a good place. You'd look at doing pressure cycle analysis on all of your pump stations. Generally, what's closer to the pump station has higher cyclic fatigue. It usually drops down below that unless you have significant elevation changes. It drops down. So there is a method there where you could begin to prioritize which ones that you would go after.
Yeah. And I would say this is it's depending on my program. So one, I'd phone friends. I'd kind of try to understand information, what's available, some lessons learned. That's kind of data gathering mode for me. And I like to be curious, so I like to talk to people. I'll learn as much as I can, and then I'll try to propose a program. And being an ILI guy, I kind of always have been an ILI guy. Was almost an engine.
So what do you feel about the potential for ILI tools to be able to find cracks and dents?
And that's where I was going, right? So I'd start trying to look at what my ILI program could be or would be, right? So it's possible I'm already doing other ILIs, i.e. ultrasonic wall thickness. It could be some MFLs, maybe some multi-data set MFLs where I have two different magnetic components looking at it. Maybe some, in this case, we heard there was some ultrasonic crack. Look and see if I can take advantage of existing data sets in place. I'd call my vendor and I would say, hey, I think I have a dent that has this profile. I could send you the radii files for it so you can understand what we think the geometry to be. Based on how your sensor carry is mounted on the tool, is there some flex there to where that's to my advantage or disadvantage if the tool is going over a dent, so that I could understand with the play associated with the dent, will my sensor carrier allow for me to get good data acquisition in the deformed area? Because a lot of times at that point, you might not even care if the sizing's right? You might just be looking for detection, right? If I detect a discontinuity anywhere in the region of the dent, whether it be ID or OD, I can now begin to risk rank these.
They didn't say, they just said that the inspection detected the crack. They didn't say what it sized it at. So what do you size the through wall crack at? So, God, honest truth, man. We're going to close on the story. What I will say is I do know from experience that Colonial undertook a massive program to address their dents, a multi-year massive program. But one of my favorite stories is, and you remember this, we generated some cracks in a pipe, 3 of them specifically.
Oh, boy.
And I knew one of them was through wall. And I called out the phased array guy and told him to size all of them. Oh, boy. And he comes back and he sizes all 3 cracks and he gives them to me. And I just look at him and I said, one of those was through wall and leak. He's like, you're kidding me. I was like, oh, no, buddy. You better go back and figure out one of those is actually a through wall crack. And the deepest he'd gotten was 50%, which is really great. So then he goes back and interrogates the data even more. And he's like, oh, it's this one because of this signal. And I just laughed. It was really good fun. So,
but I would say for the audience, because you touched on the ILI side, right? Is it's ask a lot of questions because there are a lot of opportunities there. And if you do end up in a situation where you're dealing with a high number of dents or deformations, I would say treat them all individually. Yeah. Look at any data that is or could be available. And again, don't assume the technology can do something, right? And a lot of times they may not be able to get a full spec for you, POD, POI, and sizing, but a lot of times they can give you enough to where you can risk rank them, right? Yeah. And I think this was a great case where the engineer got involved and he's like, hey, we found dents that have been leaking already. They were in these environments. Let's go dig these holes. And you could do something very similar like that in your program if you find yourself in that case.
So last plug for operators, what I will say is 1183 is about to undergo a revision. If you have strong opinions on dents, I would recommend that you reach out to API and get on board with that committee as it goes underneath revisions, because it is in need of a lot of work. The first round was a good stab at getting things in there, but it definitely needs it needs an overhaul and some operator input. So, all right. So this was the 6th in our series. We have one more episode coming up for you guys. Yeah. We'll be taking on another gas pipeline failure, and I'm going to say another, let's call it emerging integrity threat. But we hope you enjoyed this episode. We'll see you again in 2 weeks.